Hello, everyone. Welcome to our symposium, Music and Language, Two Domains in One Brain. Our first speaker for the symposium is Mary Tavini, the director of the Cicero Learning Network, University of Helsinki. Mary does research in auditory cognitive neuroscience, learning sciences, cognitive psychology, and neuropsychology. The title of her talk is Music and Speech, Two Domains in One Brain. Let's welcome Mary.
Thank you so much for this kind introduction.
Yeah.
As a psychologist and kind of musicologist and cognitive neuroscientist in training, I really love to compare the domains of music and speech in the brain. I've done it since many decades already, and in my talk you will get a kind of overview of the very basic studies, and then something about music learning in the brain, and then the key thing today, I think, is the interplay between music and language, music and speech. Very often one starts these discussions from left and right brain. We will go into that in a minute, but I want to start from the deep structures of the brain, namely those structures which encode produce emotions and mood, because those are very intrinsic for our social communication and maybe even for the motivation to listen to music. It's very emotional thing what we perceive in music, and also it's very emotional what we can produce when speaking, when using prosodic features of speech. Of those we will hear more later in this symposium. But really, already since the early studies, it has been thought that there's a specialization of the human brain in terms of left and right brain, left and right hemispheres in music and speech processing, and the very early findings were based on brain lesion studies. But already a bit more than 20 years ago, we made brain studies using new methodology. We ran one MEG study, and we also ran one PET scanning study using phonemes E and O and chords C major and C minor. And we showed that in this kind of audible sequence, those phoneme changes from E to O activated the left hemispheric temporal lobe areas, auditory cortex, and correspondingly the changes from C major to C minor activated the right side areas. And from that, we really, at least in my opinion, really objectively could conclude that also in healthy brain, this kind of lateralization, asymmetry between the hemispheres, it exists. Later on, last year actually, colleagues in Montreal made much more elegant study. They had 100 songs and they filtered either the lyrics and the temporal parts of the songs, or then the melody, the spectral features. And they showed that really also in continuous musical information, songs and melodies, the lyrics are processed on the left side and melodies then on the right side. So based on this, we can say at the same time that there is this kind of lateralization for the information, meaning lyrics and melodies, but at the same time, it's all about the sound features, temporal and spectral, which dominate the information. Speech is needs very good resolution in temporal matters, and then melodies and musical information more generally in spectral features. So this is already the first interim summary of my talk. Music has its imprints in the brain, and those can be studied in many ways so that we find the anatomical and functional networks over there. And that for music, there's the dominance of the right hemisphere. And then we go to the learning aspects. Already in 90s, it was shown that adult musicians differ from adult non-musicians in various parts in their brain, both again in terms of activity and later on also in structure. And we went one step further. We showed that also the type of musical expertise affects this encoding. So that the classical musicians display larger mismatch responses, meaning more accurate discrimination of the sounds if there's something wrong going in tuning. So mistuned tones evoke larger responses, specifically in classical musicians. And then let's take for the comparison transpositions of music examples. They evoke larger responses than in jazz musicians. And from that, we could kind of conclude that the type of musical expertise is reflected in the brain functions in MMN and P3A responses. But at the same time, we should remember that if we only study adult musicians, then we cannot know what has been there before they started their training. As well, it might be that those people who are very, let's say, accurate in pitch, they tend to start playing instruments which are then used in classical music and so forth. But in any case, in longitudinal studies, it has been shown that music training is improving auditory processes of many kinds, audiovisual integration, somatosensory and motor functions as well. So it is not only so that something is there ready and then this kind of child starts playing, but it is so that these functions are improved while training. And these skills and these processes can be called near transfer, so that those are something specific to music. But then music training has also been associated with linguistic functions, for instance, phonemic awareness, foreign language pronunciation, as well as then with higher cognitive functions, such as executive functions, working memory, and attention. I should say that these effects are kind of more vulnerable and they depend a lot on the paradigm, how they are investigated. Then there are also some findings about the relationship between music training and mathematical skills and social skills, but I still have a couple of question marks over there. We need some more studies upon those. All of these are called far transfer. By now there's also some discussion going on whether actually phonemic awareness, for instance, it's so close to music that it is part of near transfer. We will see how the conceptual development of the theories go in that respect. As an example of study in longitudinal design, I want to introduce next two studies very briefly. In Finland, we have a tradition of music play school, which means that kids are playing together with one teacher in a group, and they have something music, some kind of music activities going on, but it's very far from instrumental training. They are singing, they are clapping, they are dancing, but they are not learning any instrument. And we had this kind of children who got the music play school as part of their kindergarten activity, and we had a follow-up study of 2 years with them. And as controls, we had dancing children, and then control group, passive control group. And the findings showed that those children who were involved in music, play school activities, their phoneme processing and also vocabulary developed faster than with dancing children or passive control group. This was not reflected in the auditory brain potentials, but at least we found it at the behavioral level. A bit of similar study was run in Beijing, China, and there we had a group of school children, elementary school children, who had extracurricular activities 2 times a week. And our primary interest was originally in music children, and then as a comparison, we had active group who learned English language, and again, passive control group. And we had behavioral tests and EEG, and here I report only the EEG, mismatch negativity result, which is kind of surprising. The children who were in the English training group, their mismatch response to melody changes, it was enhanced compared to other children during the training of 1 year only. So this is very exciting, and I'm really looking forward for making some further investigation. And here, the second summary, music has its imprints in longitudinal designs as well, and there are near and far transfer effects. However, it's much less than that advertised in media. And then interestingly, foreign language training can also boost auditory non-speech processes in the brain. And finally, we go to interplay between music and speech. What does it mean? What could it mean? First of all, to start with, they both are auditory information, but they slightly differ in their important features, like I said already in the beginning. So speech is very much loaded by short scale temporal cues, and music has something to do with fine tuning of spectral cues. And that's why the left and right brain specialization makes a lot of sense. Then both are based on long-term memory. So we have memory templates for words and melodies, some of us even for symphonies and bigger entities, depending on our training. And they both, music and speech, they really rely on these long-term processes. At the same time, we should be aware of the fact that that kind of implicit learning can be traced back to the prenatal period. So we have shown that learning of sounds and sound features starts already prior to birth. And then, of course, we need to be aware of explicit training, explicit learning, which is caused by lessons in music and lessons also in languages. Then final issue, which is highly interesting, is that the languages differ in their emphasis on different acoustical cues. For instance, quantity languages such as Finnish, we can differentiate semantic meaning between words on the basis of the length of phoneme, like tuuli and tuli. Those are different words, tuuli, tuli. And then, interestingly, in tonal languages, such as Chinese, pitch level and pitch contour also then carry semantic meaning. So whether a word is pronounced high pitch, low pitch, or whether there's a change in the contour. Finally, we come to my very first slide, which told something about the emotional processes in the brain. Brain networks for language, music, memory, and emotions, they all are interconnected. So we should not rely on studies which are specialized on one domain only, But we should take all these complicated issues together, and in the very best case, do longitudinal and multi-methodological studies in order to learn how the interconnections, how the interplay there develops, be the training then in one domain implicit or explicit. After that, we can get certainly important information about the roles of these functions, both for learning applications and applications in rehabilitation. It's time to thank you for your kind attention. Have a nice conference.
Thank you, Mary, for your wonderful presentation. Our next speaker is Mirai Basson. Mirai is the research director for the Lab of Neurobiology and Cognition at Aix-Marseille University in France. She is going to talk about musical expertise and novel word learning, near and far transfer effects. Now, let's welcome Mirai.
Okay, very good. So I'm very happy to be virtually with you at this IOP conference in Beijing. And I would like to start by thanking the organizer of this for inviting me to speak with other colleagues. And I think that we are going to have a very interesting symposium. I would also like to start by acknowledging the great help of my collaborator, Mylène Barbarou and Eva Dittinger, who were graduate students with me and who did a lot of the work that I am going to present to you today. And I also like to acknowledge Stefan Elmer, who is a longtime collaborator. So basically what I'm going to speak to you today is about musical expertise and novel word learning. It's about a little bit less than 20 years, in 2004, that the first experiment on what's happening in the brain when you acquire the meaning of a novel word was performed by McLaughlin and a collaborator. And what was very interesting is that they show that the N400 is a very reliable marker of word learning. And interestingly, and that's something to remember because I will come back to that several times in the following, is that at the beginning, when you learn the meaning of a novel word, the N400 is frontocentrally distributed. By contrast, when you have acquired the meaning of the word, when it is firmly established in your memory, then you have the classic central parietal N400. And this effect has been demonstrated both when you use associative learning, that is, you associate the meaning of a novel word to a known picture, for instance, or when you learn the meaning of a word from a sentence context. So in both cases, you have an N400 who develops first over frontal region and then over parietal region. So what I've been interested in the last 7 years, let's say, is to study the impact of, last 20 years, sorry. Novel word learning is last 7 years, but the impact of music training on speech processing is much older than that, more than 20 years, I think. And it's really to see the impact of musical expertise, musical training on various functions, and I really focused on speech processing. And our team and many other teams have shown that when you are a musician, you show facilitation in various aspects of speech perception, categorical perception, speech segmentation, phonological awareness and reading, and even syntactic processing. And in this symposium, we have, as I said, expert researcher in this domain. And I just want to mention the very nice paper that was published by Professor Nan in PNAS, in which they showed in a large cohort of Mandarin-speaking children that 6 months of piano training really improved various aspects of speech perception. I think it's a very nice study. It's a longitudinal study, very difficult to conduct, and giving very interesting results. Professor Samler also published very nice work recently, more on the clinical side, and showing that children with cochlear implant really benefit from musical activities, and not only them, but also if they are singing with their parents, and that greatly improve prosodic stress perception, which is an important aspect of language, of speech understanding. And finally, Marie Tervaniemi has been conducted a longitudinal study, also with collaborators at Beijing University. And interestingly, they compare different groups of children involved either in music training or in foreign language training or in no training. And they interestingly found that foreign language training in some way had a greater impact on some auditory function than music training. So that will be interesting differences to discuss during this symposium. To come back to the project that I want to present to you today, which aim to answer the question, does musical expertise positively influence novel word learning and why? I want to present you two things. First, the results of cross-sectional studies that we conducted with children who had some musical training, 3 to 7 years, versus non-musician. Result with young adults, in this case it was professional musician compared to non-musician, and older adults, also musician versus non-musician. And I just tell you right away what the results is in case you fall asleep during my sleep, during my talk, is that we found faster and more efficient novel word learning in musicians than in non-musicians. So that's results of the cross-sectional study. Then we conducted longitudinal study to try to understand why we found this music to language transfer effect. I'm going to go fast on the cross-sectional studies. They have been published, and I'm just going to summarize the results in order to spend more time on the longitudinal studies. But I want to insist on the experimental design because that's going to be the same design across all the experiments that I'm going to present to you. First, we have a phonological categorization task. For reason of time, I'm not going to speak about that today. Then we have a word learning phase. We have a word learning phase, a matching task, and a semantic task. The word learning phase is before the test, that is matching and semantic. And we used as a stimuli monosyllabic Thai words that vary in pitch and in vowel duration. And as I said, we tested in separate experiments. We tested children who were between 8 and 12 years old, young adult, and older adult between 52 and 69 years old, and who had something like 40 to 60 years of music practice. Oh, in the learning phase, what do participants do? They are first presented with a picture and then with a word that they don't know. And they have to learn that this monosyllabic word, pa, means I in this foreign language, and that, for instance, pa mean flower. And there is no overt response. There are several repetitions, actually 20, I think, and subjects are asked to learn this meaning. And here are the results for children, young adults, and older adults. I'm going to be quick, as I say, but I just want you to notice that in musician, top row, you have an increase from first to second block of trials, so increase in learning, reflected by increased amplitude of the N2 and N4 component. And you find that basically in all three groups of musicians across the lifespan. By contrast, in non-musician, it's non-significant except for the N2 in a young musician. But overall, you see clear differences between musician and non-musician in the learning phase. So what was really striking is that you can see the emergence of the frontal N400 after only 3 minutes of learning. And then this N400 shifted to a parietal distribution within 6 minutes. So that's, I think, very good evidence for fast brain plasticity, and also that it is faster in musicians than in non-musicians. Now let's go to the test phase. In the test phase, the participants are again presented with the pictures they have seen in the learning phase. And these pictures are associated either with the same word or with a different word. And they have to say whether the pair match or mismatch. Okay, and so if we look at behavioral results, children and young adult musicians made less error than non-musicians in the matching task, with no difference in older adults. If we look at ERP, you again see that the effects are much larger in musicians, whether children, young adult, or older adults, than in non-musicians, where the effects are barely not significant, at least regarding the N400 effect, a little for the N2 effect. So here we find strong evidence in the ERP for musician and less evidence for non-musician in the matching task. Now let's go to the semantic task, which is in some ways a stronger probe of whether participants have really learned the meaning of the words, because now they are presented with a novel picture. That is, you remember the initial picture was an eye. Now the novel picture is a book, and that is related to the eye because you need your eye to read. But the subject, the participants, have never seen this picture before. But still, after book, he still hear pa, as he did in the learning phase. And pa is related, while pa is unrelated. And they have to give this response. So if we look at behavioral results, again, children and young adult musicians made less error than non-musicians. Same results as for the matching task. If we look at ERP, the results are again very clear, with very large differences between related and unrelated word in the three groups of musicians, more in children and young adults than in older adults. But in the non-musician, it's not significant in either group. So we take these results as showing that there is a stronger integration of the word meaning in musicians than in non-musicians. One thing important that I didn't mention is that here you are looking at parietal sites, and that's why we think that this N400 effect reflect the integration into semantic networks. Okay, so in sum, for this cross-sectional experiment, we find similar results. We can discuss the differences, and in particular, the less clear effect in non-musician adults, in older adults in the discussion. but overall, we find similar results in 3 independent samples of participants. In the learning phase, we showed faster brain plasticity in musicians and in non-musicians at frontal sites. And in the test phase, we showed that in the matching and semantic task, the N400 was larger over parietal sites to mismatching and unrelated words and to match and related words in musicians and in non-musicians. So that led us to conclude to the general conclusion that music training facilitates the learning the meaning of novel words. So in some way, you have an impact of musical expertise on semantic processing. Now, how can we account for this effect? That's the interesting part. Well, basically, there are 2 hypotheses. One is bottom-up processes. That is, all this is linked to cascading effect from perception to phonological representation and to semantic processing. So in some way, the idea is that better perception drives better word learning. But, you know, there are also results in the literature that show better auditory perception and attention in musicians and in non-musicians, better cross-modal integration, better working and short-term memory, and better executive function. And all these functions will contribute to novel word learning. So it's so possible that there are top-down effects that explain this transfer effect from music training to word learning. So now, I'm going to present the first longitudinal study that was performed with young adults, professional musicians versus non-musicians. And the idea behind this experiment that we discussed, and we are thankful to Ken Paller for suggesting it, is we want to neutralize differences in auditory processing and associative learning between musician and non-musician. In some way, we want to neutralize bottom-up processing. And we also want to test the top-down hypothesis by looking at long-term memory. How did we do that? It's a little bit complicated, but stay with me. On day 1, participants perform 2 experiments, 1 and 4, that I will describe later. And on day 2, they perform experiment 2 and 3. And 1 month later, they came back and they redid all these 4 experiments. So what are these experiments? The way in which we neutralized auditory perception and associative learning is by asking participants to do learning matching cycle. So they are the word learning, you know, pictures and a word, and they have to learn 5 trials. And then they have the matching task in which we present either the good association or the wrong association, and they have to say whether it's match or mismatch. And we do that until all participants, each participant in some way, until each participant perform 83 correct in the matching task. So in some way, when they arrive at the semantic task, all participants have the same level of word learning and matching. And so, in some way, if we find differences, they will not be due to perceptual processing or associative learning. So now, what are the different experiments? Experiment 1 is like the one I described you, in which we have Thai words. In experiment 2, we use easy words. Those are Finnish words linked to yenis that are much easier to process for French people than the Thai word used in the first experiment. In the third experiment, we were interested in knowing if you can associate an unknown picture with an unknown word, okay? So we created pictures that have no meaning, and you have to learn that this picture means rampu, and you have to make this association. And finally, in the fourth experiment, we counterbalance previously known association. For instance, in French, hat is said chapeau, but instead of hearing chapeau, they have to learn that in this experiment, hat is said fromage, okay, that cheese. So they have to learn a new association to counteract. And okay, so and then they have the matching and semantic task as I described earlier. So basically, when you look at the results of the learning matching task cycle, participants need 5 learning cycle to reach the threshold, and the number of cycle varies as a function of the experiment, with the large number for the most difficult experiment, the one with the Thai word, and that shows the importance of stimulus material in driving novel word learning. Now, if we look at the semantic task performed on day 1, when the difference in auditory perception and in associative learning are neutralized, there is no difference in behavior and no difference in ERP. It looks at this picture, it's very difficult to understand, but no, it's very easy because you have no difference between either in the musician group or in the non-musician group, except in this first experiment, which is perceptually the most difficult because it is with the Thai word. So the first conclusion, very important, is that when we neutralize differences between musician and non-musician in auditory perception and in associative processes, we found no difference. So the advantage reported in the Dittinger et al. Studies, the cross-sectional studies that I showed at the beginning, were likely driven by bottom-up processes. Okay, now if we look at the results on day 30, and that's very interesting, then you see that there is better long-term memory for novel word in musician in all experiments, E1, E2, E3, E4. So in all experiments, you have better memory for musicians, better long-term memory for musicians and non-musicians. And if you look at the ERP, again, in the first experiment, the most difficult, you find the parietal N400 effect 1 month later. So it means that when the experiment is very demanding, then you establish a strong memory trace of the word, and then you still find differences without rehearsal 1 month later. And that was not the case in the other experiment, neither in musician nor in non-musician. So the second conclusion is that for the first time, we demonstrated enhanced long-term memory for novel word in musician. And so that means that top-down processes also contribute to explain the positive influence of musical expertise on novel word learning. Okay, now the last experiment. So in the experiment that I just described, we neutralized the differences between musician and non-musician. In the experiment that I'm going to describe now, we did the reverse. We took non-musician and we trained them with psychoacoustic procedure to improve auditory processing and to see whether low perceptual skills causally drive successful novel word learning. So we use this experimental design. First, there are categorization tasks, but again, I'm not going to speak about it. Then we presented complex harmonic sound, and we measure pitch threshold and intensity threshold. Then we have perceptual training over 2 weeks, 3 times an hour. So it's 3 hours of perceptual training altogether. Then we measure the threshold again, pitch and intensity, categorization, and what I'm interested in is word learning and testing. So now, if we look at the discrimination threshold, then you see that participants in the pitch group ameliorate their pitch threshold. It is lower. So the threshold is lower after training than before training in the pitch group, with no difference in intensity. Now, in intensity, you find the reverse results. That is that in the pitch group, you have no difference in intensity threshold when you compare pre versus post-training. But when we compare pre versus post-training for intensity threshold, then you have a decrease. So basically, this means that the training was efficient and it was specific to the trained demand. So now let's look at the consequence of this very short pitch training on word learning of words that vary in pitch and in duration, as I mentioned, since we use the same design as in the previous experiment. If you look at the behavioral results, in fact, the only difference between group is in the matching task, where participants in the pitch group trained in pitch perform better, made less error than participants in the intensity group. If you look at the ERP in the learning phase, matching task, semantic task, you see that in the learning phase, you have the typical frontal and frontocentral N400, and that is larger in the pitch group than in the intensity group. And in the semantic task, all across electrode, but also over parietal electrode, you have larger N400 effect in the pitch group than in the intensity group, with no barely significant difference in the matching task. So in sum, the results of these longitudinal studies show that either in behavior in the matching task or in ERP, in the learning and semantic task, we have evidence for the importance of bottom-up processes in novel word learning when words are difficult to perceive, as it is the case for Thai word, and even with very short training, only 3 hours. So if you improve perceptual acuity, auditory acuity, then you may also find evidence that you improve novel word learning. So in general conclusion, what we have demonstrated after 7 years of work is that there is clearly a great importance of enhanced auditory perception for novel word learning, but we also find enhanced long-term memory for novel word in musician. So in some way, the conclusion is that both bottom-up and top-down processes contribute to explain the positive influence of musical expertise on novel word learning, but still, even if both contribute, it seems to be that there is a predominance of bottom-up processes. More generally, these results highlight interactions between perceptive and memory function, and the transfer effects that we demonstrate from musical expertise and acoustic training to long-term memory and novel word learning for us are taken as evidence that we have domain general network in the brain that underline perception, cognition, and language processing, and that these networks are highly dynamic and interactive. And on this general consideration, I thank you for your attention.
Thank you, Mirai, for your great talk. Our next speaker is Danila Zamla. Danila is the group leader of Research Group for Neurocognition of Music and Language at the MPI for Empirical Aesthetics in Germany. Her title is The Neural Basis for Intonation and Tone Perception in Mandarin Chinese. Now, let's welcome Danila.
Thank you, Yun. Thank you very much for this nice introduction. It's a pleasure to be here. and welcome to everybody who is listening and watching. So, I don't know. Okay. Does everybody see my slides? Wonderful. So it's a pleasure to be here and to talk about one of our newest experimental series on Mandarin Chinese. And I have to say from the very beginning that this is the work that has all been done by Pei Ru Qin for her doctoral dissertation at the MPI. So as we have heard in the previous talks, there is the idea that there are neural networks for language and music that somehow differ in lateralization. So we do have several areas in the left hemisphere. I've scheduled or sketched here auditory, motor, and cognitive regions that are interconnected by different fiber tracts to support motoric aspects, phonological aspects, and semantic aspects of language and speech perception. And we may have a mirror image in the right hemisphere, dual streams for music perception that involve also auditory functions, motoric functions, and cognitive functions, and are interconnected again via white matter fiber tracts. Now, that's one thing. But I would argue that there is, well, we talk about language and music as two different categories, but I think there is rather a continuum between these two domains. And this is very well visible when we look at the types of sounds that are used in language and in music. So on the one side, we have, let's say, phonemes. On the other side, on the music side, we have tones and chords. But already in speech, it gets interesting in Mandarin Chinese or in tonal languages, because their pitch that we use in music usually is used for conveying lexical meaning. So you have, as you know, in Mandarin Chinese, at least 4 different tones that define lexical meaning. And then there's a third category of sounds, I would say, and that's in the middle between the two. It's speech prosody. So if you think of speech prosody as something that is pitch related, it's not only pitch, but it's also duration and intensity. But here I will focus on pitch for the sake of simplicity. We use speech prosody linguistically to convey, for example, statements and questions. So in non-tonal languages, pitch drops to express a statement and pitch rises to express questions. And we use pitch also for expressing emotions, attitudes, and intentions. Here I brought you very different pitch contours produced by German speakers when they express a warning or when they express a criticism. So we do have pitch in speech, in prosody, and in music, and that's what we found interesting. And we wanted to know which neural networks underlie this intermediate category, so speech, prosody, perception. And we started out in non-tonal languages. In this case, we started out with English, but we replicated the results in German as well. So to localize the core network for prosody perception, we developed a new paradigm. We invited speakers to produce single word utterances, namely the word bear and pair, uttered either as a statement, you see here, the falling contour, or as a question, you here see the rising contour. Then we use these 4 stimuli and put them into a morphing algorithm to create continua, prosody continua, that gradually change the pitch contour from statement to question. As you can see here, what happens then is that in the middle of the continuum, you're not quite sure whether this is a statement or a question because you have 50% of the signal of both extreme points. I play you the continuum from statement to question of a female speaker.
Bear, 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 bear.
So on top of that, we created stimuli for a control task simply by morphing orthogonally to the prosody the phoneme, the word initial phoneme from B to P by gradually lengthening the voice onset time. As you can see here, so here is a long voice onset time, here is a short voice onset time, and we gradually increase that. When I play you the continuum, you should hear a flip from bear to pair around the third item, so to say.
Bear, 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 bear.
Okay, these stimuli were used in an fMRI, functional magnetic resonance imaging experiment with 24, at that time, English native speakers. And they were presented with the prosody continua in random order in prosody blocks and with the phoneme continua in random order in phoneme blocks. And they had to say via 2 alternative forced choice button presses whether the speaker named the object or asked for the object, or whether the speaker said bear or pear. And what we did is we simply then contrasted brain activity in the prosody task minus brain activity in the phoneme task. And what we got is a right lateralized network of regions, auditory regions along the temporal lobe, motor regions, premotor cortex regions, and what we say the cognitive regions, inferior frontal gyrus. We also did connectivity analysis, so we used probabilistic phylotractography to identify the most likely white matter connections between these regions. And these are the middle longitudinal fascicle for the ventral stream and the arcuate and superior longitudinal fascicles for the dorsal stream. And for those of you who are familiar with the language literature, they see immediately that this is like the mirror image of what we know for the left hemisphere for language processing. So they describe a ventral stream that processes semantic meaning, so sound to meaning mapping, and a dorsal stream that processes sound to motor mapping, so articulation phonology. One parenthesis, we were a bit surprised to find the premotor cortex here, because our participants, they did not vocalize, they just listened to the stimuli, but it's very well possible that they subvocally rehearsed the stimulus or imitate the stimulus to do the task, to understand the prosodic contour. Okay, so we came up with this little model saying that we have a ventral stream for auditory categorization, representation, the meaning, the semantic, if you will, semantic meaning of prosody, one pathway for motor simulation, and one pathway for the cognitive evaluation. So as I said, this is all done in non-tonal language speakers, so English speakers. And one thing that I should mention, so this is the summary slide. Interestingly, for our symposium, the right hemispheric prosody system seems to overlap with what we know from the literature about music. And this is a point where transfer effects might happen, actually. And I am in the very comfortable position to collaborate with colleagues from Finland, from Helsinki. And they do extremely interesting research. For example, finding deficits in music perception and in prosody perception once they have lesions in the right ventral stream and inferior frontal gyrus. And this is work with Aleksi Sivonen and Teppo Särkimö. And in collaboration with Ritva Torpa and colleagues, we see that musically trained children have better prosody perception. In this case, these were cochlear implant children. And this has effects on language perception. So it seems there seems to be evidence that we have music prosody overlap in the right hemisphere, which may be a precondition for transfer effects that have been described in the previous talks. Okay, but now let's look into a different topic, because as I said, this is all done in non-tonal language speakers. And Peiru came to the lab and asked herself, well, does this dual stream for prosody generalize to Mandarin speakers? Because as you know, pitch in Mandarin Chinese has dual functions. And the most important function of Mandarin Chinese pitch is the lexical tone. It's lexical information that is conveyed by the pitch contour. So rising contour on the syllable ma means hemp, and a falling contour means to scold. On top of that, there is also intonation. So I just replicated these two tones here, tone 2 and tone 4, expressed as a statement. But you do see this trend that questions are higher rising. So the overall contour of the lexical tone is preserved, just the contour is rising higher up in tone 2 and is not as much falling in, as it would in a statement in tone 4. So the question that Peiru asked, is this fact somehow influencing how Mandarin Chinese listeners process intonation? I call that intonation or prosody in Mandarin Chinese. And she used a very similar approach as we did in the study with the English speakers. She used these 4 stimuli, so tone 2 spoken as a statement, tone 2 spoken as a question, tone 4 spoken as a statement, and tone 4 spoken as a question. And she created intonation continua between these items. She also used the same tokens to produce tone continua, so from tone 2 to tone 4 in a statement utterance, and from tone 2 to tone 4 in a question utterance. And as a third condition, which we didn't have before, she also morphed from female to male voice gender, staying within the tone and in the intonation. She did this on syllable B. For those of you who know Mandarin Chinese, when spoken with tone 2, it means nose, and spoken with tone 4, it means arm. And these stimuli were presented to 24 Mandarin Chinese native speakers. And this setup of tasks allows us a multitude of comparisons, and not only tone versus intonation, but also intonation and tone versus the gender task. And this is something that is a very clever move, because sometimes it has been described in the literature that the results that you find in a specific contrast may not generalize to results you find in other contrasts. So to really find the core intonation network, it is necessary to control or to compare with different tasks. And even here we have the chance to control within task. So Peiru used the clear stimuli, so the outer stimuli in the continua, and compared them to the inner stimuli, the ambiguous stimuli, to find the real representation regions, auditory representation regions for prosody perception. And she did the same for tone for the sake of interest. And I can also tell you that we also recorded data from 24 German speakers to do a between group comparison. So it was a really huge project that she did. Okay, let's look into a few data. So first thing, if we look into Mandarin listeners, intonation, greater tone task, we do replicate the right frontal region. So right premotor and right inferior frontal gyrus. No? This is what actually matches what we found in the English and German speakers. If we compare intonation to gender, the picture already changes. So we replicate still premotor cortex and IFG in the right hemisphere, but we see that the left hemisphere is kicking in as well, so mirror image. And we see some parietal activity here as well. So it's a phonological system that we see activated here. And finally, if we look into the clear, greater ambiguous intonation, the network even becomes bigger, because now we also see what we missed in the previous slides, temporal areas. Yeah? So we see the full-fledged bilateral frontotemporal parietal system that is used for intonation processing. So this replicates, but also extends our previous findings. We didn't do DTI, so we didn't do probabilistic fiber tractography, but it's very likely that we have dorsal and ventral pathways here. Instead, Peiru decided to do a functional connectivity analysis. And she used inferior frontal gyrus as seed regions to see under which conditions inferior frontal gyrus connects to which regions more strongly. And what she found is that the IFG connects more strongly, and here come the results, with temporal regions in both hemispheres once the stimuli are clear. So once intonation is the prototype, if you will, of intonation on tone 2 and tone 4. And you also see enhanced connectivity to the parietal regions. One point we are not quite sure about yet, and maybe that's a point for discussion, is why we don't see a lot of connectivity of the right IFG. Our idea is that perhaps the right IFG has a more general pitch-related function that is reacting equally strongly in the clear and ambiguous stimuli. So it's always active. That's why you don't see the difference. Whereas the left IFG is more linguistically tuned and may therefore show this difference. So in sum, we do see, we replicate the dual streams for prosody in the right hemisphere. So we have auditory categorization, motor simulation, and the cognitive evaluation as we see in the non-tonal language speakers. But we also see that it is, well, bilateral. And we have this key region, the left inferior frontal gyrus in Mandarin Chinese speakers. For the next question, how this architecture compares to tone perception, Peru did the same comparisons. I want to cut it pretty short. One thing that we found interesting, and it replicates previous research, is that the tone processing seems to be more strongly left lateralized. So we see again these parietal areas, and we see premotor cortex, no frontal regions, no right hemispheric regions. If you compare directly to intonation, you see activity in bilateral MTG and angular gyrus, which are known as semantic regions. And this makes a lot of sense to see semantic processes in tone perception in Mandarin Chinese listeners. And in the clear versus ambiguous comparison, you see temporal regions again popping up. So in sum, we see semantic processing, phonological processing, and the motor simulation plus auditory categorization in Mandarin Chinese tone processing, which fits pretty well with what is known from the literature. So bilateral, temporoparietal, phonological, and semantic networks. When you compare tone and intonation, you see a lot of overlap in yellow here, but you also see distinctions, partially distinct. So again, the semantic processes are specific for tone, and the more cognitive controlled judgments of prosodic pitch are specific for prosody, for intonation. Okay, one final thing. I told you that we have data from German non-tonal language speakers that listened to these Mandarin Chinese stimuli. And the question is whether they use similar networks for the tonal language material. And indeed they do. So you see very nicely also these auditory categorization regions, phonological processing, the premotor areas, the cognitively controlled processing of pitch. But there are also slight differences. For example, you see here stronger involvement of cognitive control because the stimulus material is unfamiliar for both tone and intonation. And what is interesting also, of course, you don't see the semantic processing of tone in the German speakers. So to sum up, if we look back at our continuum, we were covering phonemes, or well, tones and speech prosody. We find plenty of overlap in Mandarin Chinese listeners and also in German listeners, which tells us that at least these yellow regions are core areas for the categorization of pitch-related information. So they are not specific for intonation, prosody, and tone, but they are maybe more general regions, which probably generalize also to music, which may be the basis for transfer effects that have been nicely shown by Yunnan in her lab. So between tone and music, so to say. This is the anatomical basis, and of course, a lot more studies have to follow to really tease out the details. But with this, it's time for me to thank you for your attention, and I'm looking forward to the discussion. Thank you.
Thank you, Daniela, for your excellent talk. Our next speaker is Sun Chen. She is a PhD student in my group, studying at Beijing Normal University, China. She is going to talk about the development of musical rhythm and its relations to reading development in school-age children. Now let's welcome Sun Chen.
Okay, hello everyone, I'm Sun Chen, and it's my pleasure to be here and share this work with you. In this study, we focused on children's rhythm ability and its relation to their reading-related skills. The relation between music and language has been attracting our attention for a long time. And researchers, especially in the symposium, have investigated this relation from different aspects. Let's have a quick look, and some have already mentioned in their own talks. In this article, Maria Besson and his collaborators have found that musical expertise could transfer to new word learning in children and young adults. This advantage was confirmed by EEG responses. However, musical expertise advantage was not observed in older adults. And in this article, Maria Tavanini and his colleagues found that under certain circumstances, foreign language training was able to foster children's auditory and music neurocognition. This effect of language training was in a manner comparable to that of music training. When investigating the cortical tracking of comparable rhythmic structure in both music and speech, Daniela and his collaborator has found that within participants who had less music training, they had comparable cortical responses to music and speech rhythm. However, longer music training could increase the cortical tracking to rhythm in music, but not in speech. These results imply that music and language are closely interconnected while they still preserve domain-specific features. The relation between music and language is so sophisticated and worthy of further investigations. So back to our study. Recent years in the field of child development, many studies have demonstrated that rhythm perception and production are correlated with reading-related skills. And more importantly, there are some longitudinal studies indicate that earlier rhythm abilities could predict later reading skills. This relationship has been found in diverse populations, such as in preschoolers, in school-age children, and even in children with and without dyslexia. The relation between rhythm and reading is sometimes obvious. We can easily see the positive correlation between them. The higher rhythm ability, more capable in reading skills. To further investigate their relationship, researchers usually conduct hierarchical regressions to see whether the rhythm ability has unique contribution to reading skills after controlling other variables such as age, IQ, and working memory. When considering reading-related skills, previous studies usually concerned two levels. One is the fundamental level called phonological awareness. Another is more comprehensive reading level. Phonological awareness refers to the ability to identify and manipulate small units of sound. Although the specific definitions of phonological awareness might be different across orthographies, the importance of phonological awareness for reading skills has been established across orthographies, including in Chinese. Previous studies have found that rhythm processing is linked to both phonological awareness and reading levels. However, these studies are almost focused on alphabetic languages such as English. Chinese represents an interesting contrast to alphabetic orthographies. We have tone, we have lexical tone. The different tones gives the same syllable different meanings. And study also showed that tone awareness plays an important role in reading development. So here we want to ask, does rhythm reading link also exist in Chinese Mandarin? And does music rhythm could predict phonological awareness, tone awareness, and reading skills? Before we answer this question, rhythm ability also worthy of our attention. On the one hand, beat perception seems to be innate. As we see here, after 2 to 3 days of their birth, newborn infants show brain responses to omission of the strong beat in a rhythmic sequence. This suggests that our brain can form temporal expectation and find violation at a very early stage. But the development of rhythm might be a protracted process. However, from the existing evidence, it is still unclear how rhythm processing develops during childhood. In previous studies, when considering rhythm processing, they used a variety of rhythm tasks, investigating different aspects of rhythm processing. Nevertheless, most of them mainly focused on behavior level and lacked for longitudinal data. So here comes another question. How beat perception develops neurally and behaviorally during childhood? Therefore, in present study, we followed a group of typically developing Chinese children from age 9 to 11 to see how beat perception develops, and then investigate how beat perception relates to phonological awareness, including tone and reading skills. We have 47 children. They were assessed at both age 9 and age 11. For rhythm ability, we chose beat perception task. We collected both passive EEG data and active behavior data. The stimuli was continuous beat sequence. EEG and behavior tests used the same core unit. The standard bar was a 3-note bar with the first note as strong beat. The standard duration of each note was 500 milliseconds. And for the small deviants, the duration of strong beat was 600 milliseconds. And for the large deviant, the duration of strong beat was 660 milliseconds. For reading-related skills, we tested character recognition, reading fluency, and phonological processing, including tone discrimination, phoneme deletion, and rapid automated naming. Besides, we also collected control variables such as nonverbal IQ, working memory, and their personal music training experience. So let's see the results. First is about rhythm development. At behavioral level, we can see from age 9 to 11, children got significant improvement in both small and large deviants. At neural level, the mean amplitude of P3A for in small deviant had significantly improved. Thus, we can conclude here, at both behavioral and neural levels, beat perception developed steadily from age 9 to 11. When considering longitudinal rhythm reading links, we conducted hierarchical regressions. We have 4 dependent variables. They were all collected at age 11. And all the predictors were collected at age 9. In model 1, we first enter general cognition and then the rhythm measures. When predicting reading level, we also controlled the phonological processing, and rhythm measures were entered at the last step. Model 2 is autoregressive model. The first step entered the autoregressors. The autoregressor is the same index as dependent variable collected at age 9. For example, if we want to predict tone discrimination at age 11, we first enter the tone discrimination at age 9 and then enter the rhythm measures. And in both Model 1 and Model 2, rhythm measures were interchangeably entered at last step. Thus, we could examine the unique contribution of each rhythm measures. So in brief, Model 1 examines how rhythm at age 9 predict reading-related skills at age 11, and Model 2 examines how rhythm at age 9 predict the development of reading-related skills from age 9 to 11. So here's the results. At phonological awareness, we found that after controlling musical training experience and general cognition, behavior rhythm measure at age 9 could uniquely predict phoneme deletion at age 11. In autoregressive model, both behavioral and neural rhythm measures accounted for phoneme deletion. Similarly, both behavioral and neural rhythm measures at age 9 could predict tone discrimination at age 11, and different neural rhythm measures predicted tone discrimination in autoregressive model. Yeah. Here we find that both behavioral and neural rhythm measures at age 9 uniquely predict tone discrimination. Considering that rhythm and pitch as different components of musical processing, they might have some inherent association. And the link between rhythm and tone may simply due to the fact that the tone is based on pitch. So in order to further examine this possibility, we rerun the hierarchical regression and controlled for effects of pitch discrimination. Here's the results. As expected, pitch discrimination significantly predict tone discrimination. And after controlling that, neural rhythm measures still accounted unique variance in tone discrimination in both models. Thus, we can conclude that both behavior and neural beat sensitivity could uniquely predict tone development. And more importantly, the neural beat sensitivity could still account for unique variance in tone development after controlling for pitch discrimination. At reading level, we found that neural rhythm measures could predict character recognition in both models. However, we didn't find rhythm measures have any unique contributions to reading fluency. In previous studies, researchers found rhythm abilities had association with oral reading fluency task. But here, we used silent reading fluency task, which may minimize the speech rhythm requirements involved in overt articulation and thus reduce the effects of the rhythm perception. So to put all results together and get along with previous studies, we find that the link between rhythm and readings are developmental. We find that rhythm ability at age 9 could not only predict reading skills at age 11, but also predict the development of reading skills from age 9 to 11. And the rhythm reading links also exists in both alphabetic and non-alphabetic orthographies, and in both typically developing children and as well as children with dyslexia. Thus, our results provide experimental evidence for musical intervention in reading. And here, we also find that more neural rhythm measures than behavioral measures could predict reading-related skills. As we see here, the colored are all the significant predictors we found. The reds are neutral measures and the yellows are behavioral measures. The neural measures might be more friendly and more objectively than behavioral measures. They were less affected by emotion, motivation, or attention status. Especially in our study, the passive audible paradigm even doesn't need children to pay active attention to the rhythm. Thus, reading development might be better predicted by a combination of neural and behavioral rhythm measures rather than by behavioral measures alone. Finally, our study may provide essential neural evidence for the auditory temporal sampling theory. We find not only behavior, but also rhythm measures have unique contributions to phonological awareness. Theoretically, beat perception and phonological processing are inherently related because both of them rely on brain's ability in fine-grained segmentation of continuous input information. And this might partially explain the rhythm reading link. Above and beyond phonological processing, we found neural measures, including both MMN and P3A, continued to account for unique variance in character recognition. These results also support the abstract prediction hypothesis and the dynamics of attending theory. That is, the rhythm reading link represents a common brain mechanism which involved predicting information in metrically structured sequence. And MMN and P3A together might serve as biomarkers of brain's ability to form temporal predictions. To sum up, our study has found that the development of beat perception is protracted process in Chinese typically developing children between the age of 9 and 11. And both behavioral and neural measures of beat perception were unique longitudinal predictors of phonological awareness, including tone and character recognition. And that's all of my presentation. Thanks for listening.
Thank all of our speakers in this symposium for their wonderful presentations and great effort in contributing to this virtual IOP conference. And thank you all, dear audience, for your interests in our symposium and our talks. If you have further questions or comments, welcome to our Q&A session on the 9th of September on Thursday from 7 p.m. to 7:30 p.m. See you then and enjoy the conference.